Thank you very much. I would like to thank the organizers for this nice conference and also letting me speak in this conference. And yes, so today I'm going to talk about a project which is a joint work with Nancy Abdallah, who's online, Tony Yarubino, and Alexandra Siciliano, and Joachim Yamego, who is not here today. So this is about the strong Lefschetz property of Artinian Gorenstein, so algebras of codimension trees. So we have seen some results already in this conference about that. So already in the previous talk, we saw that there are already some work in that in this topic, and I wanna focus on these kind of algebras and try to prove the strong Lefschetz property for the ones with low Sperner numbers, Sperner number at most 6. So let me first review some of the results in codimension tree. So we already saw that for complete intersection, special class of Artinian Gorenstein algebras of codimension tree, in characteristic 0, we have the weak Lefschetz property. So, but so I'm not listing all the results in this, all the results about the codimension tree AG algebras, but the ones that I'm going to use for proving our results. So I'm for example, we recall the result that AG algebras of codimension tree and socle degree at most 5 have the strong Lefschetz property. So this is in a paper by Boy, Migliore, Miroroy, Nagel, and Zanello. And also, so we have some results about Artinian Gorenstein algebras that are presented by powers of linear forms. So those also have the weak Lefschetz property. So that's a result by Alexandra and Hal Schenk. And also, so I'm just not listing them here, but I just remind these important results. Sorry, that we can reduce the case of proving that every Artinian Gorenstein algebra of codimension tree has the strong Lefschetz property. If and when we can reduce this to the problem of proving that every compressed Artinian Gorenstein algebra of codimension tree has this property. Compressed means that the Hilbert function is maximum possible up to the middle. So that's again the result in the same paper by Voigt, Miller, Miroroj, Nagel, and Zanello. So one more thing that I want to mention here is that this is actually in the paper that I'm reporting today, that let me write it like that for a fixed H, which is a Gorenstein sequence. Gorenstein sequence means that this can be a Hilbert function of some Artinian Gorenstein algebra. So for a fixed H, there is a Zariski open set of Artinian Gorenstein algebras with Hilbert function equal to H, satisfying the strong Lefschetz property. So we know that in codimension tree, generic Gorenstein algebra has the strong Lefschetz property. This is the problem. I should move to the other one. Yes, so that's because by a result of Diesel, we have that the scheme of Gorenstein algebras with a fixed Hilbert function is irreducible. And then because the strong Lefschetz property is an open condition, we need to find just one Gorenstein for each sequence, for each Hilbert function that has the strong Lefschetz property. And that is true because we can find the one with the dual generator that is the sum of powers of linear forms. So that's the result in the other paper by myself. Okay, so the goal today here is that is to prove that every AG algebra of codimension 3 and Sperner number less than or equal to 6 has the SLP. So I should here say fix the assumption on the characteristic of the field. So in all the cases I need the characteristic, all the things I mentioned, I need the characteristic to be 0. And for our purpose, I fix this assumption, and let's for now assume that the characteristic is 0. Then I might comment on that and see if we drop this assumption, what will happen. Okay, so I want to show that, but then we have we can list all AG algebras or all Hilbert functions with this assumption. Okay, so the list of by a result of Stanley, who showed that every Hilbert function of AG algebra of codimension 3 is an psi sequence. We can actually list them based on that. So this is the list of all Hilbert functions. So just to remind, the definition of a psi sequence is that the sequence should be symmetric, unimodal, and differentiable. So the first difference is an O sequence, which means that it's a Hilbert function of some Artinian algebra. So then if you just write down what possibilities you have based on that, you get that these are all the Hilbert functions we need to study in order to prove the main theorem. So let me list them. Okay, so we have 7 sequences that correspond, and they correspond to every Gorenstein sequence of the Sperner number less than or equal to 6. And yeah, and those are all. So I will try. So let me see. There's no assumption on T, meaning that T can be anything, 0 and 1 and larger. So my goal is to try to give the idea of proving how proving this main theorem, but I mean not for every Hilbert function we need a different idea, or maybe for some of them some idea works. So I want to list some of the previous results or some of the main ideas of how we can prove such a result. So the first thing, which is the first result that I want to mention, and it's due to Yarovino and Koniev, is that if we have, so let's say K, the field is infinite, and let your algebra be the quotient of a polynomial ring in 3 variables. And assume that the Hilbert function of your algebra is something like this. So it goes up to S, and it has repeating entries of S for at least 3 times. Okay, so if you have such an assumption for the Hilbert function, then we can, I mean, they show that there is an ideal of points in P2 that is equal to the original ideal in degrees here and before. Okay, so let me write that. Then there exists an ideal J, which is equal to okay. Okay. Yeah. No worries. Okay. Okay. So yeah, we can. There exists an ideal J which is equal to the ideal I in degrees where we reached the first degree that we have S and plus 1 and less. Okay. Such that J is saturated. Ideal defining scheme of S points in P2. So that means that the Hilbert function of J is equal to this sequence here, to Hilbert function of I, and stays S after that. Okay, so this, and then of course I is just a quotient of ideal J, but this is important for proving the maximal rank property of some of those multiplication map, because we have it for the ideal of points. So let me write down a lemma or corollary of this theorem. So, but in general, if we have such a situation, not necessarily in P2, if you have this kind of quotient of ideal of points, then as I said, we can prove that some of the maximal ranks have some of the multiplication maps have maximal rank. Let me see. Yeah, okay. So that's let your ring be one-dimensional, where where J is as above, then there exists a non-zero divisor for B, which forces to have a maximal rank for these maps. Where I is between this degree and the middle. So my A is as before, so then you can find such J. So then you have this, this multiplication map has maximal rank on B, but since the algebra is equal to these degrees and lower, to the degrees of tau plus 1 and lower, so that means that you have the maximal rank or A for these degrees as well. Okay, because that's just equal to the ideal of points. Did I do something wrong? Okay, so that is useful for proving that here, if you have T at least 3, so for the middle maps, we have the maximal rank property by this lemma and the theorem. Okay, so then the main or the thing that is left to prove that when T is 1 or 2, and also the other maps for when it's constant. So then I just wanna tau is the first degree that the Hilbert function reaches S. So then, by this well-known theorem by Gordon and Noether, we can, I mean, they showed that A for AG algebra of actually codimension less than or equal to 4, the multiplication map by J minus 2 from A1 to AJ minus 1 is isomorphs. So this also has maximum rank by Gordon Noether's here. So now again we know that the map from degree 1 to degree J minus 1 by that result of Gordon Noether has maximal rank, and from degree 0 to degree J is also trivial. So that's yes. Oh yeah. Yes, thanks. Yeah, J is always the socle. Yeah, I mean, yes. So there is one form, and then it is yes. Yes. So then it remains to show that first for T at least 3, there exists L such that the maximal, multiplication map from AI to aj minus I from degree 2 to degree tau minus 1 is isomorphism. When t is at least 3, and when t is 1 or 2, then so we need to show that, so that can be actually included in the previous one. So basically, you need to see what tau is, where the first degree that the Hilbert function reaches to the Sperner number, and then so you know the degree 1 by Gordon-Noether, and prove degree 2 up to degree tau or tau minus 1 by these are left to be done. Okay. When did I start? Okay, so did I start 45? Okay. Okay, so then by those two theorems, the corollary is that, I mean, immediate corollary is that when the Hilbert function is equal to 1, 3, S, 3, and 1, for every t has the strong Lefschetz property, right? So when t is at least 3, then we have nothing to prove. So when t is 1 or 2, we have low socle degree. That so the socle degree is at most 5, and we know it by the results, previous results. Okay. So let's say we have an algebra. So this is not necessarily codimension 3 algebra. So we have an AG algebra of codimension n. If there exists one L such that linear form, such that this algebra has Hilbert function almost constant Hilbert function, so it's just 1 and then S, and this algebra has a strong Lefschetz property, then A also has the strong Lefschetz property. So this is actually done by looking at the short exact sequence that we have by the multiplication map by L. So we have this short exact sequence, and then we can multiply by L vertically, and then if we know that these two vertical maps have maximal rank, then the middle map also has maximal rank. So this is saying more than just assuming that this algebra has a strong Lefschetz property. So that's this result is using that every Artinian Gorenstein algebra with this Hilbert function has a strong Lefschetz property. So, and knowing that, going back to our the proof of our main theorem, by knowing that, we can show that every AG algebra with this Hilbert function, if Hilbert function is equal to 1, 3, 4, 5, so increasing by 1, maximum by 1. So every AG algebra, so that actually this Hilbert function forces the strong Lefschetz property. So how do we show this is that we can, so again, to just, right, so if T is, sorry, if S is 3 or 4, it's already covered by the previous results. So we have nothing to show. But if S is 5, then here we have 2 generators of degree 2, right? But then because of this 5, S is 5 at least, so we can usually, for any S, at least 5. There is a linear relation among those two. So, because otherwise the Hilbert function cannot be this. So then, relation. So then, I in degree 2 can be up to the action of general linear group can be this or x squared and xy. Okay, so we have only those two for the degree 2 piece of the ideal, those two generators, and that means that if I let L to be just the linear form X, then we have, if you look at the colon ideal, then either this ideal inside the colon ideal or X and Y, right? So either we have this or that in any of those cases, right? So then this means that the colon ideal or the quotient by this ideal by colon ideal has Hilbert function 1, 1, 1. That satisfies that property, and it's almost constant. And the quotient by, so that means that a Hilbert function, and when you just mod out by X, this is codimension 2 algebra, and then it has the strong Lefschetz property. Then we can go back and use this result and say that, okay, this algebra also has the strong Lefschetz property. So it's just by looking at the degree 2 piece, and so this has the strong Lefschetz, this has the strong Lefschetz, and then we use the short exact sequence to say that the middle one, which is the algebra, has the property. Okay, so let me just see, like, let's see what we have done so far. So we have proved this, and then increasing by 1 is the one we just did, and then this is also done, and this is 1, 3s, so that's yeah, somewhere on the board, and that's this. So this is the only thing that is left. So, and which is the hardest Hilbert function. So let me just, before giving the idea of proving that, see that what do we need to do based on those the middle boards. We only need to prove the Lefschetz from degree 2 to degree socle degree -2, right? So from 5 to 5, because that's Gordon-Noether, and the middle one, oh, actually, when t is equal to 1 and 2, we have to also do the middle one as well. Not for 1, but for t equals 2. For t larger than 2, then we can use this result. So I erase this one, or maybe I don't have to. Yeah, so let's see. We have we want to show that these forces strong Lefschetz property. So that's the theorem and completes the main theorem. So we can first assume that the socle degree is at least 6, right? Because for 5, you can use the result over there. So J is at least 6. And right, so now again looking at the degree 2 piece here. So we wanna prove this map. We wanna prove that there is a linear form such that this map is an isomorphism. So look at degree 2. So we have one generator of degree 2 in the ideal, and then there is one generator of degree 3, which in degree 3 we have these elements. So G is not in the ideal generated by these 3. Okay, so then F and G have to have common divisor. I mean, they don't have to, but let's say we consider the case when they have common divisor. Okay, so then that common divisor, so we have degree 2 element, degree 3 element, has to be a linear form. So they, let's say x1 is the common divisor. Right, so then now F prime is degree 1 element. So then again, we can use the short exact sequences and look at this. These algebras, and since we have codimension 2, here we have codimension 2 algebra, here again colon ideal, which has F prime as a generator, is codimension 2. Those two have cell P, so then A has the cell P. So we are done in that case where we have common factor over those. So then the hard part is that when they are a regular sequence F and G, and then the algebra A, the original algebra, is a complete intersection. So F and G being regular sequence forces to have, so F and G regular sequence implies that there is H of degree J-2 inside the generators of I. So then I is generated by F, G, and H, complete intersection. So it has to be in this degree, the next generator, because that's the degree when it's 5, and then it cannot be later because of the symmetry of the resolutions. Okay. Okay, so here let's define one new algebra, which is just one-dimensional algebra that we just quotient out by f and g. And since this algebra is one-dimensional, then there is an open set in, let's say, S1 of non-zero divisors, of non-zero divisor elements. LU is non-zero divisor on A prime. Okay, so, and so we have that the rank for this map, and I mean, so let's see, we have that A prime and A are equal from degree, some degree J minus 3 and lower. As vector spaces, so all of them are equal. So then, so because we have this non-zero divisor on A prime, we have maximal rank property for these degrees and before. So for everything ending here in degree J minus 3, we have maximal rank property by that. So what we need to show is that we wanna say that this is isomorphism as well. So from degree 2 to degree J minus 2. So this we don't know. So that's 1 degree after what we know. So, but assume that this is not. So assume L to the J minus 4 times Q, which Q is something in degree 2, is 0 in A, but it's not 0 in A prime, right? Not 0 in A prime. Okay, but then there's very nice idea in a paper by, I mean, this part of the proof is using the embedding of some projective spaces into the power series ring, and then it allows us to write them as power series. So here there is an open set where we have this linear form L, and we can prove that for each L there is unique element of degree 2. So then we can just vary this L, meaning that we can have L as just varying T. We can have L as it changes by T. And then for each one, we have one unique degree 2 generator of the algebra that is equal to 0. And then writing this as a power series by the embedding that I'm gonna skip the technical part. For every V. So this is 0, and then you can look at the different degrees, and then the degree 0 gives you, I mean, coefficients of P0, or the constant is just the equation we have, and then coefficient of T is equal to something very interesting, because then it corresponds to the multiplication map by L to the power J minus 5. Let me write it down. Okay, here we have Q naught. This is the coefficient of T, and that is 0. So we can factor out L to the J minus 5. that corresponds to the map from a 3 to a j minus 2, or by symmetry from degree 2 to degree j minus 3. Okay, so this means that there is a one-dimensional kernel in this map, which we know the map, but then it also implies that the dimension spanned by this is also one-dimensional, because this is the kernel of this map, and this is one-dimensional. That means that the dimension of this also is one dimension, one, right? So then, okay, so I should skip the technicality here, but that uses, I just want to emphasize on that, that this uses this map that is one-dimensional that we know, and then since we have this space one-dimensional, then we can see that we can there is a relation between this and the generator F. But then this implies that I mean, then you can continue working on this element, and it implies that we get to contradiction with the complete intersection, because of this fact that it was not zero in A prime, and so I just wanted to just tell you that there is something here that uses geometry, and it was in the paper by Bricali, Favelle, and Pirola. So they use geometry to prove something about the maximal rank property in degree 1, and it's very useful when we get to these kind of situations. So I think the method can be even used for other cases. Okay, sorry, I'm over time, and thank you. That's it.